Hello, good evening everyone. Again, welcome to PG Physics classroom. So, this is Pratibha, the, as you know, the coordinator, PG Department of Physics. Yesterday we discussed how the finite mass is affected on the spectrum of beta ray, that is neutrino mass is how it is effective for the beta ray spectrum. Now let us discuss with the topic the allowed and forbidden beta transitions. So we will calculate here log ft values. So later I will tell you what you mean by ft. Log ft values, depending on these ft values we are going to uh, differentiate the forbidden and beta transitions. Okay, getting my point? Then okay, now let us start with allowed and forbidden beta transitions. Please write down the equations. While I am explaining, please note down the equations. So wait a minute. Okay. Fermi's theories of beta decay gives a relationship between the decay constant of the nucleus and the maximum beta energy. So now integrating equation 5724. So think 5724 is that is yesterday's equation. I will show you. Wait for a minute. 5724. Okay, this one. That is what? Probability distribution. That is g square divided by, please note it down. G square divided by 2 pi cube c cube h cross raised to 7 into matrix element square f of z comma pb square am minus ab whole square into dpb. By referring this equation we will continue. Okay, so now let's come to the next slide. Just wait for a minute. Okay, getting confusion. It's 49. Okay. So the Fermi theories of beta decay gives a relationship between the decay constant of the nucleus and the maximum beta energy. Now integrating that equation, as I shown you the equation now, so we get the total probability per second of the emission of beta particles of all momenta from 0 up to maximum probability. 0 up to maximum. The Fermi's theories of beta decay gives a relationship between the decay constant of the nucleus and the maximum beta energy. As you can see, the lambda exists in the previous equation in 5.724. So if you integrate that equation, we get the total probability per second of the emission of beta particles of all momenta from 0 up to a maximum probability distribution. Okay, now 50, where is 50? Okay, moving on. So keep that equation is number 1. So that is equals to, by referring those equations, c into integration of 0 to p, the maximum probability. So whatever the left parameters are, f, which is the function of atomic number, and the probability distribution of beta particles, pb square am minus eb square into dpb, where c is equals to this constant. You can see in the equation number 5.724. Okay, the integration is most conveniently carried out by using the following transformations. Let us write epsilon beta equals to eb by me square, eta b is equals to pb by me c. Put this is equation number 3. Equation number 1, 2, 3. So here epsilon beta and eta beta are dimensionless forms of the beta energy and momentum. Now using equation 5.33, we get that is EM minus EB. EM minus EB is equals to that is difference in work function WM minus WB. Again, in terms of the Einstein's theory of relativity, I will write here PM square C square plus ME square C raised to 4 minus PB square C square plus ME square to C raised to 4. So now evaluating here, see, as I told you that, so ME into C square they have taken common. What left is root of 1 plus eta m square minus root of 1 plus eta b square. Why? Because see, you can see here, just writing PB is equals to PB is equals to eta B MEC into ME into C. PB is equals to, by using this equation, see, eta B, PB is equals to eta B into MEC, putting that values and evaluating the expression, what we will get, that is ME square ME into C square taking common, what left is root of 1 plus eta m square minus root of 1 plus eta b square. Eta b is equals to PB by MEC. Okay, similarly eta m is equals to PM divided by ME into C. Now the subscript m refers to the maximum beta energy and momentum. Then, so again the equation becomes this much, integration of f function and PB square, again PB square, putting the value of EM minus EB and squaring, and after evaluating what we will get, this much. Just write down the equations, and into ME square into C raised to 4 root of 1 plus eta MI square minus root of 1 plus eta square whole square into MEC into d eta. Just evaluating the expression, that's it. So later, finally, whatever the equation found, just note it down. Equation number 4, 5.84. For low z elements, this function f of z comma eta equals to 1. So then we get lambda is equals to 0 to eta m 1 plus eta m square minus 1 plus eta square into eta square into d eta. So this is equals to 1 for low z elements. Thus the probability of beta decay increases with increasing value of matrix element. The factor multiplying f of eta m on the RHS side of equation 5.85 is a constant if matrix element is assumed to be a constant. Since the total probability of the disintegration per second is nothing but the decay constant lambda is equals to, as you know, 0.693 divided by tau, where tau being the half-life, we get g square by using equation number 5.85, g square c raised to 4 me raised to 5 divided by 2 pi cube h cross raised to 7 into mif square to f of eta m is equals to lambda is nothing but what, 0.693 divided by tau. 0.693 is nothing but what, ln 2 divided by tau. Now f of eta, so this is, so writing these terms in this side, so hence the function of eta m into taking this tau into this side, so then rewriting the expression f of eta m into tau, f of eta m into tau is equals to 2 pi cube h cross raised to 7 into ln 2 divided by g square c raised to 4 me raised to 5 into matrix element square is equals to what, this is something constant. Okay, put this is equation number 5.86. okay, now the value of the constant on the RHS of equation 6 depends on the square of the matrix, element, which in turn depends on the wave functions of the parent and product nuclei, as also on the strength of the weak interaction causing beta decay. The product f of eta m into tau is known as the comparative half-life. The product, these two parameters productively called the comparative half-life. The product of f of eta m into half-life is known as the comparative half-life. The equation 6, that is 5.86, shows that for larger value of matrix element, the comparative half-life is smaller. For the larger value of matrix element, the comparative half-life is smaller. So small value of the comparative half-life indicates larger probability of beta decay. So that is larger lambda and vice versa. The comparative half-life can be estimated by evaluating the integral in equation 5.85. This is evaluating. So just evaluating this equation 5.855. Okay. See the product. So this is very important. Please do remember. The product of these two parameters f of eta into tau is called as comparative half-life. So which is larger, which is large for smaller value of f eta tau. Which is small for larger value of matrix element value, and which is small for larger probability of beta decay, and vice versa. The comparative half-life can be estimated by evaluating the integral equation 5.8.5. Okay. So that gives f of eta m is equals to integration of 0 to eta m 1 plus eta m square minus 1 plus eta square into eta square into dm. Okay. Now let us move into the next slide. Okay. Oh my goodness. 123 plus 124. Okay. So again evaluating the expression. So what you will get? That is this much, minus 1 by 4 eta m minus 1 by 12 eta m cube. These are the experimental calculations. 1 by 30 eta m raised to 5 plus 1 by 4 into root of 1 plus eta m square ln into bracket eta m plus 1 plus eta m square. So now this equation 5.87 gives approximate limiting values for f of eta m for large and smaller eta m. So eta m is very greater than 5. So hence f of eta m is nearly equals to 1 by 30's time of eta m raised to 5. When eta m is very less than 0.5, so this value relatively equivalent to 2 divided by 105 eta m raised to 7. So these are approximate limiting values for these two conditions. Okay. Between the limiting values, f of eta m, that is comparative half-life, has to be calculated by using the more correct formula by using this equation 5.87. So as shown in the table 5.1, the values of f of eta m for different eta m, you can see 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 1, 2, 3, 4, 5, 6, 7, 8, 0. So different f of eta m function values you can observe here. Okay. So in the calculation of f of eta m above, we have assumed a plane wave for the electron. In however, the distortion due to the Coulomb field is taken into account. The factor f of the factor f of z of eta must be retained in the integral equation as shown in the previous equation. The integration then gives a function in place of f of eta m, so that we get f of z comma eta m into tau, so which is equals to constant. This is very important topic whatever we are discussing today. The constant on the RHS involves the matrix element MIF square, which as we have seen cannot be evaluated exactly. For allowed transitions, this is usually taken to be unity. For allowed transitions. Using the value of the integral by equation number 1, we can estimate the comparative half-lives for different nucleides from knowledge for their half-lives. This helps This helps us determine the constant G, giving the strength of the weak interaction. In the values of log Ft are calculated for different beta emitters using the experimental values. Ft is nothing but what? The comparative half-life. So log of Ft for different beta emitters using the experimental values of Pm and tau. Then the values are found to be grouped in certain regions as shown in figure. See here figure. On the basis of such grouping, we can broadly classify the beta emitters into different categories as follows. Okay, see here. This is log Ft value. Please draw a graph. I will explain you later. So, number of cases versus log of Ft. Distribution of log Ft values 3 to 4, 5 to 6, 7, 8, 9. Okay, I will explain you. Please draw this graph. Okay, 3 to 4, 5, 6, 7, 8, 9. So now let us move to the next slide. Okay, so first one, the log of Ft value up to 3 to 4. So wait a minute, I will show you I will take a snapshot. So I will show you while explaining. 3 to 4. You can see here log of Ft value 3 to, in between 3 to 4 I am explaining. So what happens here? Sorry. This explains log of Ft 3 to 4. The beta transitions are most probable for the nucleides in these groups. They are called allowed and favored or super allowed. The number of nucleides in this group is relatively small. Okay, 3 to 4. In between 3 to 4, we can say that the beta transitions are most probable for the nucleides in this group. They are called allowed and favored or super allowed. The number of nucleides in this group is relatively small. Later, the log Ft value from 4.5 to 5. In this case, the beta transitions are allowed but not favored or simply allowed. Their number is the largest. The probability of the transition for these nucleides is lower than for the point number 1, 3 to 4. So this is lower than the point number 1. So log of Ft value from 7 to 9, these constitute the first forbidden transitions. The transition probability being lower than that for 1 and 2. So 3 to 4 and 4.5 to 5, the allowed transitions are exhibited. Apart from that, from 7 to 9, these constitute the first forbidden transitions. The transition probability being lower than that for comparatively small for 1 and 2. For still higher values of log Ft values, so above the value of 9, we get forbidden transitions of higher order, for which the transition probabilities are still lower. Okay. The above classifications of the transitions is not always very clear cut and rigid, as will be evident from as shown in the figure. So in this below table are included some beta emitters listed according to their log Ft values. Okay, so first decay transition, you can see here hydrogen beta negative decay transition. The half-life is 636 seconds. The maximum energy range is 0.783 and log Ft value is 3.08. So again this value comes under what? Log Ft 3 to 4. So hence the transition is super allowed, or you can say the favored transitions. Similarly, this case, all, so these all transitions exist in between the log Ft value 3 to 4. Hence these all transitions are super allowed transitions. Now from this one, so this is the value chloride, which is silicon, which is giving the beta decay emission. So this is simply the allowed transition, because this comes under this group, that is simply the second group, 4.5 to 5, simply the allowed transitions. Allowed, this is also allowed transition. And letter from 7.08, here you can see log ft value between 7 to 9, these constitute the first forbidden transitions. Hence this is first forbidden, this is also first forbidden, forbidden, first forbidden, first forbidden, first forbidden, first forbidden. So letter greater than the first forbidden range. First forbidden range is nothing but what? 7 to 9. Above the 9 value, what you will say, that is 14.5, 18.5, there are second forbidden transitions and third forbidden transitions, like that. The classification of the beta transitions as allowed or forbidden is similar to that in the case of radiative transitions in the atoms, being governed by the value of the matrix element HIF for the transitions. As we have seen, HIF includes the time dependent perturbing potential, which depends on the electron and neutrino wave functions. Assuming plane waveforms for leptonic wave function of beta and leptonic wave function of neutrino, we can expand them as an equation, as we have discussed in earlier. In the previous discussions, we retained only the first term in the expansions, which is just unity corresponding to allowed transitions. In this case, the emitted particles, that is beta or neutrino, do not carry any orbital angular momentum, so that del L equals to 0. The successive terms in the expansion fall off by a factor of kr into r divided by lambda cross, where r is the nuclear radius and lambda is equals to 2 pi lambda cross is the de Broglie wavelength of the emitted particles. For the beta disintegration energies of the order of 1 MeV, so r divided by lambda cross is nearly equivalent to 0.1, so that the successive terms in the expansion decreases by a factor of about 1 divided by 10. So I hope up to this you understood. You read it once. This is very important. So they will definitely ask for 8 to 10 marks. How the beta transitions can be categories are differentiated depending on the log ft values. That graph is also very important. This table is also very important, and these 3 points are also very important. Please do remember this, and once again read it and solve the derivation. So while solving the derivation, you understood. So because this is the easier one, so it looks tough, but while solving the derivations, this is very much easy to solve the equations. Okay, solve it and come to the log ft value is the f into t, the product which is called as what? Comparative half-life. Comparative half-life. This is very, whatever the topic we discussed today, that may be come in the exam for 10 or 8 marks. Please do remember. So okay, up to this, I hope you guys are clear with the subject. So again, I will be back with you soon. Until then, take care, stay home, be safe, and keep in touch with the books and teachers. Bye. Thank you.